Okay, great. Now we're good. Okay, so we're back to it. Bold text, I'm going to say this is a digital 2022 workshop called the yeah, just like this. So whatever that's in the star is going to be bold, and then let's say I'm going to write like a um, and now we have this Digital Futures 2022 workshop, contextual assembly, and then as in subtitle is the TSNE grid maker demonstration. Okay, so once you mounted your drive, you can connect this. You can make directories or change directories, do whatever you want as far as the your file structure goes. And the Google Drive, you can make changes. So that's what we're going to do right now. So before we do anything, we want to make sure that it is in the correct directory. This CD, that definition CD, is to indicate where your folder is located. Okay, so CD /content and the drive. We are already on the drive, but then we're going to make sure that we're on the My Drive. It already knows what I'm trying to do, right? So sometimes it will auto finish it or complete. And for the this particular workshop or for the TSNE in general, we want to make a separate folder in your Google Drive. In my case, I already have this folder called the call app TSNE in my drive. But you don't have it, you don't have to make it manually. You can just code that into your Google Call app. Okay, so for making directory, it's exponential expression mark with the MK. This is short for make, and then dir is short for the directory. So make directory called collab TSNE. You can call it like this, or you can call it like this, up to you. But you have to remember what's the folder name that you're calling it. Okay. So for me, it says make directory cannot create directory call up TSNE file exists. It already exists. So for my case, this is unnecessary, right? But then for you, once you click this and then check your My Drive again, then you would see Google Call App TSNE folder in your Google Drive. Okay. Any questions or any problem so far? All good. Yeah. Okay. Just to be kind to ourselves, I'm going to make a note here. This telling myself low is to or define the directory and to create folder for TSNE, right? So it's explaining what I'm doing here, and I'm going to add another line of code below. This is going to actually make another set of a folder inside of the Google Colab TSNE. You saw that in my Google Colab TSNE, there is a TSNE, a grid master folder, and then there are some other folders that I made and then put in as a part of the setup. So here, the same thing. This is a little bit repetitive. There is a shorter way to do this, but then I wanted to make sure that everybody understand this step by step. So to avoid any confusion, I'm choosing this way. Okay. As it's the same content drive and then my drive, and then there is another one, right? We just made it. Call that TSNE. Right. Now we defined it. Define the directory, and now we're going to make directory TSNE. Right, so now we have the directory, and then now again we're going to change the directory to so now we click this, then no such file object. Cool. Content drive, my drive, call it TSNE grid master.
Thing is the D in drive, it should be capital D.
Oh yes. Thank you. Yes, perfect. Thank you for catching that. I will make a lot of a spelling mistake today, so please bear with me. And I'm going to say make TSNE grid master inside of TSNE. Right? And also we find again, or again to the folder. Okay, the next one, we're going to predefine certain conditions for this demonstration, which is Tensorflow. Tensorflow, have you guys ever heard of the Tensorflow? It's one of the largest research group that's doing a lot of machine learning AI studies. They're under group of Google, and then a lot of the machine learning that we currently know as GAN, like style GAN, cycle GAN, VQ GAN, or whatever GAN you name it. They're mostly like 95%. They're using the TensorFlow as their kind of a core structure to process their data. So to call out the TensorFlow, it's actually going to be percentage because that's in this specific environment, the Google Colab. TensorFlow is already integrated to the Google Colab the environment, so you don't have to actually import or anything. So you just need to change your directory. TensorFlow version. There are TensorFlow 2 and then a more newer version, but then this particular code was optimized for the 1-point version instead of a 2-point version. So we're going to call it out 1.x. What 1.x means is that if you have played a game or let's say version of a Blender or a version of whatever software, there's always update, and then this is like a big update, and then this is a small update. To be specific, we're going to use actually 1.15, but then defining just 1.x is fine for now. And here we're going to add another text to explain this. This is to make sure we are using version 1.x. Okay. So we're going to run this, and then now TensorFlow 1.x is selected, and one of the benefits to you of using the Colab is not just giving us this environment, but then it will let you borrow the Google servers graphics card. So to do that, we I want to do this below, which is here. To do that, we want to make sure that a GPU is connected to your system. So to check this GPU underscore info, this is a function that's embedded in Google Colab, so you don't have to call out anything. NVIDIA no, I didn't mean to do this. NVIDIA SM. Am I making spelling mistake? Yeah, we don't like this. Okay, let's see what happens after we write this code. And this is with the backslash n. And all of this information, actually, when you go to the this one by Google Colab. Using Colab. Yeah, right here. So this is the more of an extended version of it. But what we want is actually, we want to check what kind of GPU we're connected to. This changes from time to time. Now this should work, and expression and video as well. Yeah, let's one join info, GPU info. This just like displays the what kind of GPU that you're connected, and if GPU info find. This is just to build a failsafe to your system. And whenever we're using quotation mark, this is a string rather than integer. So it's some text information that is used as a signifier. When there's a no GPU information found, that means it's like more than, when there's a failed GPU find more than 0, then you're printing not GPU, and the else GPU. No, we have to actually define this again. Else is the opposite of the if. So if let's say you divide world into two, and then the if belongs here, and then else is the everything else that's other than this specific case. It's pretty similar to human grammar, but just a little bit more specific. So what this does is that if it fails to find the GPU, then it will say it's not connected to the GPU, and otherwise it will show us the GPU information. Join GPU info from okay, we're not connected to the GPU. That's why this has this issue. So when you having this issue, go to the runtime and then change runtime type. There is a hardware acceleration, and you select the GPU, then you're good. Runtime shape, because I'm using Google Colab Pro, I'm going to choose a high RAM, which is letting me use the higher capacity of the RAM for my Google Colab session. But if you don't have Pro, just use the standard for now. Okay, so we're good. You have too many session, active session, menu session. So if you have a more than one open, you are not allowed to use more than one GPU at the same time from one account. So in that case, you have to make sure that you're only using one session that you need for the GPU. You can do many different sessions for just the CPU only, but then if you're using the GPU, you have to allocate only one per your account. Now we're running this again. Print GPU info. Here, I did something dumb, which I shouldn't indicate this as the string. I should have indicated this as the function, because this is a function. See, this is now connected to the GPU. Let's see what I got. I got Tesla T4, very expensive graphics card. We're using it for free. But you see what I did here, right? Like if you make this as a string, it will print literally GPU info. So that's not very helpful. So don't do that. Delete the quotation mark, and then it will give you all this useful information. So now I'm very happy with the GPU that I got. So I'm going to keep going, and I will make a note here saying this is to check. Okay, so you're now connected to the GPU. And the next one, from here, we're going to actually write the core code for the TSNE. There are many libraries that we're going to use, but then we don't have to use all of the library. Yesterday, when we covered the TSNE example, there are these types of libraries that we imported to run this type of a simulation, right? And we're going to use we're going to do the similar thing, but it's a little bit more complex. That's all. So I'm going to disconnect this, and So here, now we're serious about making coding. Okay, so before actually I go into that, I want to explain what we're going to make a little bit more theoretically, so that you guys know what we're like trying to build here. Yeah, like these are many images, so maybe it's a little bit hard to explain, but here you can see that this is a grid condition. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 by 10 condition. So how many images do you think that you need to fill out the 10 by 10 images? You need at least 100 images, right? From here to here, this is the 10. From here to here, this is 10, right? And each of these images, let's say this is 128 pixel, square pixels. That means each one of these blocks are 128, right? If that's the case, 128 multiplied by 10 equals 1,280. So one length of the x, if this is x-axis, if this is y-axis, you can demonstrate the size of this whole thing as a 1,280 by 1,280, right? So this is the size, but then as in size of the image, size of the grid is 10 by 10, and then the size of the original image is 128. So let's say you have 1,000 images in your image bank. Then what's the maximum number you can run in your run as a grid condition? For the 10 by 10, you need 10 by 10 is 100 images. You at least need 100 images to run this 10 by 10 grid, right? But let's say when you have 1,000, what's this number x going to be? Well, you can guess it probably. You can probably get around like 30 or a little bit above, right? Because the 30 multiplied by 30 is a 900. 30 squared is a 900. So you can do 30 by 30 grid with no issue when you have 1,000 images, right? So these are some of the core information, core mathematical information that we need to know before we build this code, right? Use how the TSNE sorts out the images and then to make the correlation between this image and that image. We don't have to code that. It's already developed by this amazing guy that I introduced you to yesterday. So we don't have to worry about it. What we need to worry about is the how these are shown in a grid aesthetic, and how that's represented, how the TSNE is represented in this like image assembly manner, right? So with that note, this is the everything that you need to know mathematically about this code. But there is another information. So let's say you have 1,000 images, then all of 1,000 images are if for the eyes of the computer, this is just a random information that's like floating in the air. It's like a dust in the air. You don't know what it is. You just know that there is something here. So for computer to understand this very well, you need to make each individual particle or each individual image to be exactly the same size, exactly the same format. So we're going to enforce that through this code that we're going to write. So first, let's say there is like a maybe particle that looks like this, maybe particle that looks like a triangle, there's a particle that looks like a circle, there's a particle that looks like I don't know, some irregular shape. But then we actually always want exactly this square within this object. So we're going to enforce that. Then after that, you have all these square objects that's that has been, let's say, filtered through this process. But then this is not everything that you this is not the everything that you need to do. There is another step. For computer to process it easily, you need to go through another filter process where everything goes in like this inside of this funnel, and then this funnel will split one cube at a time, and then it will make an array of a cube as a list. And then from here to there, this is a, let's say, because computer counts from 0, the computer doesn't count from 1, okay? So this is object number 0, object number 1, object number 2, object number 3, object number 4, and so on. And then it will go up to 999 object number, so that it can have a list of the things, very organized, hyper organized, so that it's ready to work. So this is going to be another process that we're going to code through this, write through this code. So these are two main things that you need to know about this code. You will understand this a little bit better as we move into the actual writing a code part. So don't worry about it if you don't understand it right now. But as I do the coding in the Google Colab, if you don't understand certain things, or if you're curious about what this certain element does, please ask me a question so that I can know how much you follow, how much you don't follow. I know that there are variations in the skill sets in this class, but I want to make sure that everybody has some understanding of what's happening. I don't want you guys just use the code that I gave you and then click buttons. That's not the point of this workshop, right? And is you want to learn what's happening. So, okay, now we're ready. We're ready to really make a serious coding. So as I said, this requires many libraries, unlike the other ones that we covered. So first of all, Python doesn't know how to do math. So we need to teach it how to do math by importing a library. And then for that, it's called the NumPy. It's a very cute name, NumPy. But then typing NumPy every time that we use NumPy is annoying. So NumPy as NP. That's quite common in any the coding, any other coding, not just me, but everyone else is using this tool. This is the most basic. And then there is another tool that is quite useful to make like shortcuts, almost like a shortcuts. Import and the OS and our sparse. Make sure this is correct. Okay, doesn't like it. What did I do wrong? Our parse. This creates a argument for an object. So what these two tool does is that it makes an aliases. So you know in Rhino when you use a certain function very often, that Control J is like for join, and then Control G is for group. It's very much like this. It's not like you can press keyboard and then Python will do something for you. But then, for instance, this is also aliases, right? But then argparse will universally shorten, let's say, for instance, later on we're going to use like a dir is short for directory. Directory is very handful, and then there's a higher chance to make a typo. So we want to just use a dir instead of a directory. Even sometimes you use D instead of a directory. So the library is for this type of purposes, and of course you need the TensorFlow. So TensorFlow as a TF. So these three things, almost always you will use this. Almost always. TensorFlow missing N here. TensorFlow, and there is another one called the image. IO. Image IO is the most common image tools that you will use for loading your images, saving your images. So this is also very useful to have if you're learning, if you're using, if you're doing any sort of image-based machine learning.
What is OS argparse for? What is that?
I just explained. So this argparse, let's go to, let's actually look it up. Argparse. This is Python. Argparse. So this is a Python's all the functions or explaining what each individual library is doing. So argparse. Here, what does it say? Argparse module makes it easy to write user-friendly command line interfaces. The program defines what arguments it requires, and argparse will figure out how to parse those out of a system argument. And the argparse module also automatically generates help and usage messages and issues errors when user gives the program invalid argument. So it is to, let's say, define parser and argument. You're like defining all these, let's say, variables, but then also at the same time, it's giving you a help command. Like, so help integer for the accumulator. This is something that that will pop up when you're writing a message in your thing. Like, for instance, image IO, like it pops up as image IO. Like if you write down your syntax or the let's say like a shortcut with the argparse the function, it will pop up as an autocomplete function, and also at the same time there are some other things that you can do. For instance, this //sum is now a new aliases for the summation, like plus. And this explains what this function does. Help sum the integers, right? It explains what that function is exactly doing. So it's making aliases, it's making a shortcut, it's like creating an interface for us to work easier. When you have a very short code, this is completely unnecessary. But then if you have something more complex, you want to have this interface set up for you so that later on your life gets a little bit easier. Does that make sense?
Yes.
Okay, great. So image IO, we did image IO, and then this is something that we already used last time. It's the matplot library. So this is mathematical plotting library basically, and we are using matplot library as a ML. So you see all these like the messages that was popping up when I was writing. That's the actually the using the art parts is that very similar. It's giving a very similar definition of for all these like aliases that you're going to set up. So we're going to call this MLP because this is too long. And within the matplot library, we're going to also use pyplot, and we're going to call it PLT. Pyplot is the like a kind of a whenever you don't know something, you can always search it up. Enter to the pyplot matplot library. Pyplot is a collection of a function that makes matplot works like MATLAB. MATLAB is a mathematical coding tool that's often used by scientists and the engineer, and then this creates figures that looks like a scientific looks like something that's right out of the scientific journal. If you're coming from scientific or engineering background, you probably recognize this kind of graphical styles. Okay, so we are importing all these like mathematical tools and the PIL. This is also another image tool. We're only using image part of the PIL. The PIL is actually a larger library, and then image is kind of a tool within the PIL. So here, this is image module, and it's called, I think, some like pillow something. What is it? Yeah, pillow. So the pill is for the short for the pillow, and then the within that pillow, there's the module that is called the image. You can think this as an, let's say, history section in the like actual library. When you go to library, there's architecture section, there's a landscape architecture section, there's a I don't know, like a art history section, and this is basically pulling out just like a small portion of this PIL library as a small section, so that you're working in that discrete environment rather than trying to bring everything that belongs to PIL. This kind of practice makes your program run a little bit faster too. Okay, PIL, we covered that, and then from Web JV, this is a very like peculiar type of the library. We might have to actually install it manually into the Google Colab later on. It's very technical and then math heavy, so I'm not gonna go into the detail why we need this, but this is basically, you can understand this as it's like helping you solve complex mathematical equation a little bit easier without thinking too much. Okay. From sklearn manifold. This is also something that we covered yesterday. This is the guy who developed the PCA and the TSNE. He made this whole library for the everyone who wants to use the TSNE algorithm. So we're going to import the TSNE within his library. So this is the library. I mean, this is to be absolutely correct. This is called API. API is here. Like application programming interface. You know, like this PC is in hardware, and then now you have a monitor, and then now you have a window as an operating system, but then you have to install Chrome, you have to install Rhino, you have to install unzip function unzip function applications, and all these things. It's basically what you're doing with the API is that you're bringing whatever tool that you need to your environment. So you can think your this coding environment as you're creating a new world, and then in this world you want math, you want organization, you want TensorFlow, you want to play with images, you also want to mathematically plot, you also want to have another sets of image tools to play with. So you're almost like designing a game that's going to be very enclosed system. You're going to have a tree on exact location, and you're going to design an interaction between tree and your character. It's very hyper specific. So these are all API. These are API. A lot of the computer science people develop these the APIs, and then we as a designer or more of a let's say design researcher, we would use these developed tools to make use of these codes in the creative manner. And within the API is let's say the highest. I mean, there's actually the coding environment, and then there's API, there's a module, and then there's a function. There are like this type of a hierarchy. So this NumPy is API, and then where is it? It's a matplot library is also an API, but then we're just calling it as an MLP. But then here matplot library dot py plot is something that's included in the matplot library API that is a function. So these are the py plot is included in the matplot, but then we want to be specific about using this function and then call that as a PLT. That's why we're calling this out individually. Okay. So that's good. And
sorry.
Yeah.
In LabJB, we don't specify what we import.
What was that?
In line 8, we don't need to specify what module we should import.
When you go look at the LabJB, this is a very specific function already. This is literally doing like just linear assignment problem solvable using Jonker Bolgen algorithm. So we are not going to use this many times, and we're only going to use once in this code. And this is not like a large library like TensorFlow or the NumPy. So it's okay to not call it out any modules or the aliases. If you want, you can call it LJ if you're super lazy about it, but I don't think that that's necessary because this is such a small thing.
Okay, thank you.
Yeah. But if you want to be specific, you can also call LabJB from the LabJB, import the LabJB. Okay, so yeah, we can keep it like that for now. There's a thing called a Skippy And then this is also another mathematical tool that is hyper specific to this thing. It's at Lab JV. So Skippy is spatial distance. Within that, the module spatial distance, we're going to import the C distance. This is within this, let's say, space. There are like different points in this vector space, and then what this is trying to do is something like this. What's the distance between here to there in the vector mass? So let's say this is 1 0. No, it can't be 0. 1 1 1 2, and then let's say this is like 5 6 or 0 5 6. Then what's the distance between here to there? Like it's something like this. It's not exactly this, but then to just give you easy explanation, this is what it's trying to do. So we're going to use this, and we're going to also use the Tensorflow tool. Tensorflow has this like another small library. It's not actually small. It's like fast library called the Keras. Keras, if you're using machine learning tools, you in most cases you are going to use this. And TensorFlow, Python, Keras applications. Okay, no typo here. And within that, we're going to use specifically BGG16. Okay. Okay. Did I make a typo here? TensorFlow, Python, Keras, applications. It should be okay. Cannot resolve this. Okay, TF. So because we already defined the TensorFlow as a TF, we actually have to use the TF convention rather than using the full name, I believe. Okay, but let's leave this as is now, and then we're going to come back to it if this persists as a problem. I actually don't think that's the case, but. And yeah, from here, since we already like brought the Keras, the BGG16, we're going to be more specific about this. So Keras, I think I have it open here. Keras is used for a lot of image-based machine learning, and then it's very powerful API to process your images. Like for instance, like automate a lot of process, like flattening your image or make your image array, and just the process that I explained. There are like bunch of like weird shapes of an image, and then you make that as a rectangular image and then make a list of it. Keras is really good at this. So we're borrowing this tool to make those images line up and then organize so that the machine can understand and process it faster. Okay. We're going to keep adding more stuff from the Keras. For some reason, this doesn't like. So you see, like here, I am using the TensorFlow, Python, Keras processing, and then within pre-processing, within the pre-processing tool, we're only going to import the image part. And in that we already imported this part, right? So in that specific image category, we're going to also just import the image data. These are something that you don't have to understand, just need to know when to use. And this one, the Keras models, it's when you have model, model is acting almost acting as an some sort of a container, and you can embed certain functions within it. For our case, we have models. So model is an empty tray, and then the sequential means that we're going to build a feeding machine to this tray. So there is like a feeding machine that's going to keep delivering certain material into this tray, so that it is feeding it in a loop. That's why we want to use this. You can imagine that this would be quite helpful when we are trying to prepare the image sets for the grid condition. We have like thousands of images, and you can importing your images one by one after you process it with the Python Keras processing image. So there is your original image that you prepared, and then it getting segmented by the processing sketch code that we developed. So this is a splice. Once that's spliced, this individual small thing is becoming your image input for your the code, and then this is predefined for our case as a 128, 128. Once that's defined, now we know that this is what we're inputting into the machine, but then we need to go through the Keras to really make this image that we prepare to be cut out exactly in the shape and exactly in the format that we want. And then this will organize every images as an array within the list. And what I mean by list is that in the list, you know exactly what this image is. You know exactly what this image is. Of course, when there are only 4 images, it's easy to tell. But then what if there are like 50,000 images? Then can human remember where exactly is the, let's say, 40,001 the images in the list is hard to tell, hard to remember all this, right? But then Keras is making this all the process automatic. So whenever you call, if this is a list and then your list length, so let me pick a different color here. So let me go here because I'm getting full here. You have a list, and then you have a let's say 1,000 components in your list. Then your length of a list is equal to 1,000. And if you, let's say, name that out, it's going to be 0, 1, 2, 3, 4, blah, 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 and then it goes to 1000. And then in the case of image, number 0 in this list will correspond to exact image, and then number 3 in this cell will correspond to another unique set of an image in this list. So this import model sequential is in a very idealistic world or a very simple world. It's a feeding. It's making a feeding machine for your bucket. Okay. Any questions so far? And here the layer one is very similar to Photoshop or Illustrator. You have a I mean, what you see in the Photoshop is always like this, right? Two-dimensional top view of all the image arrays. But then in reality, what's happening in an Axon is that all these images are overlapped to each other like that. And then it contains all the pixel information behind one layer to another layer. What this flatten does is that we compress this into one single image. So it becomes much less complex of a data, very simple, and then very light image structure than the one that you have usually in your computer. So we finally finished importing all the library that we need for this code to run. So now we're going to call out the GPU configuration. Yes, you don't need to know what exactly it's doing. You just need to put it in whenever you need the GPU. So now we call out the GPU to be used in our code. And now it's time to use the arg parse. Parser is equal to whenever you're adding a new argument, you say add underscore argument. It already suggests this option here in the box, right? And what we want to use, I already talked about it before we start actual coding, right? There is this array or grid. We want to know what's the size of the grid. How many steps is it going to be, right? So is it going to be 10 by 10 or 20 by 20, 30 by 30? Depends, right? That's the first thing to define. So we're going to call this S for short, and then size for longer, the explanation. And this is whenever you give this variable setup, you need to define what kind of type it is. So it already knows what I'm going to do next, right? Type. What's the type of this information? It's always going to be even number, right? It's not going to be any decimal number. is going to be even number because we're going to be using grid condition. So in that case, the type of this information is an integer. So type equal int. That's the what we need for the size. And the help is to basically indicate or explain what this size is doing. This I'm going to call it size of or size. Right, this is the size of the grid. Next one, we're going to set up what are we going to do? To feed all these images or to make this grid condition, we need these images, right? But where are we going to bring this from? We need to indicate where all these images are located in your computer or your Google Drive, right? So we need to define the directory. And we're going to call this D. We're going to call it dir. What in this case? What's the syntax here? What's the type of the information here? There are in here. It says already integer, string, or float. What is it going to be? This is the directory. Any volunteer?
String.
Yes, thank you, Carlo. So it's going to be string, but then we're going to, in the Python, string is spelled as str rather than the string. So I sometimes confuse myself between the Java and Python. And here on this case, I'm going to explain and next, what else do we need for this? We're bringing the image, but to define the total size of this, we need to know what's each individual size of these images, right? So for that case, for the images, that's called resolution, right? It's a 128 pixel by 128 pixel. So in that case, we're going to call this resolution, and here res. Resolution is always an even number, so that's also integer. And I'm going to annotate it. We put images. What else do we need? When it finished making this image, we need to know what this entire thing is going to be called. When after you process all this the images, it's going to output one image file, right? And that it needs to have a certain name. So we need a name for the output file. And for that, we're going to use n as one, and name. Name is going to be the name is going to be the name of the output file. And what's the type for this? This is not integer, so it's a string. You see the difference between the string and integer? integer is an even number, not divisible, not decimal number. It's like 1, 2, 3, 4, 5, 6, 7, including 0. String is like human language. Like it's like directory of an image of a folder. This is a string. Whatever that's inside of this, the quotation mark will be always string. You can also use some sort of like a variable inside of your the string. For instance, I am, let's say, plus. Oh, actually, you don't need plus here for the Python. I am name if you're doing this, and then let's say name is equal to John and Yifei and Carlos. This is actually a list made of the strings, and then you can run this name through, let's say, you remember the for loop that we covered? For I equal 0, I plus plus, I, and if I is smaller than 3, you keep running. Then what you're going to end up having is that the I am John, I am Yifei, I am Carlos. So this is the kind of a difference between the variable and the string. This also, you can say, like, instead of calling a name, you can do what could be done. You can also do age. When you do age could be also in a list. Let's say John is 30, Yifei is like 25, maybe Carlos is like 27, and you can go through this list, and then when you run this code, it will say, I am John 30, and I am Yifei 25, I am Carlos 27. If you do for loop inside of the for loop, of course, it will say, I am John 30, I am John 25, I am John 27, and then I am Yifei 30, I am Yifei 25, I am Yifei 27, I am Carlos 30, I'm Carlos 25, I'm Carlos 27, because it's trying to see all the possibilities that you could have within this. But then there is a getaway from that. You can specify or whatever the list that you're extracting from. But we're not going to cover that. I just wanted to make sure that you understand the concept of the string and then the integer, and then also how you use that in a different situation. Integer is to call out a specific number, like an even number, and the string is to call out the, for instance, like directory or name or the language that's more approachable and understandable by the human ear. So let's go back to the making the name. So this is the name of the output. But then for this one, what if you don't have name? What if you forgot to put the name on your file? Then actually this is quite critical, because computer already finished the job, but then it doesn't know what to do. You don't have a name. Like you can't have an empty thing and then have a, let's say, JPG. You need to have a something here. So if it doesn't know what to put as a name, it will just forever be in standby. Like it will be stuck here. Just like one of those like a stupid game characters that's stuck in the wall, that's trying to walk out of the corner. Like it's just to keep bashing on the wall. Douche, douche, douche. It's like this. So to avoid that situation, we want to actually define another condition here. Default. Default, we want to set this up as the, what should we set up? We're going to call it test.jpg. Okay. Why is that? Okay, I'm missing a comma as well. Okay. For the rest of these things, we can also set up the default size, default directory, default resolution to avoid any sort of annoyance. Once you set up certain things, you don't want to change every time, right? So in that case, maybe size, you are probably going to change it every time, right? Because you want to test out different things. So maybe size, we don't need to define the default. And then the directory, every one of you will have a different directory in your own setup. So I wouldn't define it. And also in our code before, we already set up the directory here. So it would be unnecessary to set up the directory in the code, right? So we would skip the directory as well. But then for the resolution, I think that it would be beneficial to set up default resolution, because without knowing resolution, the code cannot run. So it will always try to put itself on a limbo, or it will keep giving you error messages. So to avoid that issue, I'm going to just set this as a default to be 128 pixels for the one of the dimension for your the cutout images. Okay. And name we already gave it. And what's the next one that we need? We also need to define where this the JPG file is going to be saved, right? Which is the out directory. If it doesn't know where to save, what is it going to do? It doesn't know what to do. For this one, I'm going to just say, what should I say? P, yeah, P for path. Yeah, path. And it's going to be string, right? Because it's also going to be a directory, basically. Equal. Yeah. So we have that. Now we're going to set up specific variables for the TSNE. And for this one, we're going to call X because the variable is called the perplexity. We already covered it yesterday, but I want to remind you one more time. You remember, based on the different perplexity, it will have a different level of order, or the chaos, and perplexity is the factor that kind of controls the level of a chaos. And the perplexity is spelled
Amore, che stai registrando qua?
what was that, Angelo? Did you say something, Angelo? Okay, maybe not. Maybe she's talking to somebody else. Right, equal, this one is going to be in number, so integer. This one is the perplexity. And this is actually quite crucial number, so we don't want to miss it. I want to set up a base number, and I'm going to set it up as 50 for now. And there is also number of iterations that you can run. Iteration means that you have certain lengths of algorithm, and then you run it once, you run it twice, you run it 3 times, you run it 4 times. How many are you going to run? Is this going to increase the accuracy? Is it going to produce the repetitive pattern? This is why we oftentimes use iteration to validate your algorithm. Usually more iteration means more accuracy and so on. So it's a good practice to have this in your variable. It's one of the required variables to be defined in the any function. So we're going to put it, and this is also integer, so type integer. And we're also going to define, because this is one of the required variables for the TSNE to run, we're going to put 1000 as the default for now. And for health, I'm going to mute Angelo for now and come back to it. This is the number of iterations in TSNE algorithm. So now we define all the variables. Sometimes putting all this library and then defining all the variable takes the most time, because you need to actually think about what you will need and then what kind of things that you need to calculate, and you need to design the process a little bit ahead of actually going into the code. You need to think about it. You need to do the dot exercise, that experiment in your head. So I'm thinking about all the potential things that can go wrong, or potential things that I will need. So these are the things that we need for sure for the rest of the code writing session. So we have all this, but then to build, let's say, to extrapolate extra variables that's derived from this, I'm going to add another paragraph that's defining these like necessary variables. Parse equals parse dot parse. I'm basically calling out all the things that I listed over here. What I did right here is that they're making some sort of an empty bucket with for the argument parser, and then within the argument parser, I added all of this argument, right? So in terms of a hierarchy, this is kind of a title page, and then it makes all the bucket put in here, and all of this content went right inside. of this like argument parse to visualize what this is doing. And then we're calling this out as in calling all of this out all together as a arg s. Okay, so we have that arg s called out, and in that out res is, we already defined what res is, right? Out res is literally means like a output resolution. And then we know that the args, this this ontology here, right here, args, is this group of groups of an objects, and then we're calling resolution. We're calling it out, and then defining that as a out resolution. And out name equal args name, same thing, to plot this is I'm going to explain this in a second. NP is a short for the numpy, and then we're going to use, it's a mathematical function square, you know, square root the out dimension, which is the what is the dimension? Where is the dimension? Dimension. When you have this overall one, two, three, four, five grid. We have a 5 by 5 grid. That means we have to have a 25 images in this, right? To plot, we need the at least 25. So this this equation is related to that. It's not complete yet, so I'm going to we're going to come back to it, and then I'll explain it furthermore in the later part. Perplexity is equal to the args current, and the TSNE iteration is equal to args iter. You see, the inside of this argument, there is a perplexity, there is iteration, and we're calling it out, and then we make that as a perplexity, we make that as a TSNE iteration. Does that make sense? Anyone who's lost or fell asleep? You fell asleep, John. Okay, we're good. Okay. And in the I want to build a more fail-safe for this to not fail in any circumstances. So I'm going to say dim output dimension equal when output dimension is equal to 0, false. It's going to raise a flag. It means when there is only one image, can you make a relationship to another one? To make a relationship, you need at least 2. But in our case, because our the code is operating in a grid condition, you actually at least need 4 images to make a TSNE. Does that make sense? So if you only have 1, your computer will get super confused, and then like it's going to think, oh, like how can I make a relationship from one thing to exactly the same thing? I can't do that. Why is my owner asking me to do that? And it will go in keep loop and then keep trying to resolve this issue, and then your computer will basically bug out. So we don't want to put your computer or Google's computer in that situation. So we're writing this when output dimension is 1, we don't want to actually proceed, and we want to raise a flag, red flag. We're going to be so kind and then tell you that, oh, this is not possible, don't do this, right? This is basically that. When there is a error, we're going to give you an error message. Okay, and I want to write a few more failsafe here. If paths exist, when already a path is defined, it's fine, but then if not, this is another function, argument type error. When there is an error in your directory, it's going to say this is what you typed in the directory, right? So in reality, this in like a more of a simple world, it's like this. In directory, so whatever you input is going to be in this form, and then we're using small quotation mark. Sorry if it was too small for you to follow. And now I just realized if this is the case, not valid directory, right? So it's going to yell at you. You didn't put the right thing, so please put the right thing. That's what it's saying. And here, I just told you that in here we can use. It's going to be the in there, right? So to indicate that, we're going to use format. And make sure that you have a 2 parentheses closed out here, so that this parenthesis for this one and then this parenthesis for this one. All right. What are some other issues? Yeah, same thing for the outer, right? So I'm just going to copy and paste this, and then to say this actually this needs to be inner, not outer. Sorry about this. So this is for the inner, this is for the outer, in directory and the out directory, right? So we have, I think I built all the failsafe system. So now we're ready to actually build our model. So in the Python world, you remember in the Java, it was void, and then you void, let's say like a setup, and then you make the parentheses and then make your function here like this. But then in the Python world, it's a little different. It's called the definition. So def, and we are going to use this build model. Build model is one of the functions that we brought from the Python Keras models. So this is to establish like a foundation for everything to be built on top. right? Here we're gonna make sure that you have two tabs so that your build model and then all the things that you want to have it included in your model is inside of this line, okay? Build model, we are going to make the base model first. Base model, same thing, is one of the functions that's embedded in the class. And we're going to define the base model to be BGG16. Did that happen? As okay, exactly this one, BGG16. And we have to define its weight, and we're going to call it the image net. When you go to BGG16, there are these variables that you can predefine, but for our purposes, just using the weight of ImageNet is the most important. So other things we're not going to define it. All these are already a default value or in the BGG16, so we don't need to redefine it. If you're a control freak or a control maniac, you can write this down, everything, every variables. But if you trust me, you can just leave it as is. And we're going to use a sequential. Here we have this sequential borrowed from the Keras model, right? Sequential. Is everyone doing okay? Everyone following? All good? And I'm going to explain the base model and top model just a little bit. Base model is like it's like a pancake, and top model is like you're putting some sort of like a shell, or it could be an icing on top of the pancake. So it's getting like a overlay on top of the base model, and then whatever that was in this base model can go up to the top model. And then this is always like a basis of everything. It's like a foundation, and the top model will receive the characteristics of the base model to the top model, from the base model to the top model. And sequential is something that you would do it over and over again to create this top layer to be a decoration that is made out of the characteristics of a base model. So top model ed, we're here where we top model ed, and here we also brought the image tool called a flatten, because we want to make sure all these images are exactly same size, exactly same format. So we want to use this function called flatten. Flatten has a bunch of variables to be defined. First is going to be input. Is base model. So ImageNet is this BGG ImageNet is base model, and so BGG16 is basically the input image shape, right? Does that make sense? So if this is the top model, this is the base model, and within this there is a BGG16, and then the what we're calling it here top model add is that we're going to put another wrapper called the flatten, so that all of this gets like flattened into one giant sheet of a very plain canvas. Okay. We actually haven't defined every variable. Model, base model, but here input shape, base model. We actually want to only use the output that's getting spit out from the base model. As I just showed you, B T F, right, and this is 3GG 16. We actually don't care about whatever that's the content that's this B is creating, or whatever content that's already in as an original image. We only care about what's getting output from the B to the T layer, right? That's why we want to only harvest the output of the base model, instead of using this like a whole base model as the whole body. We only want like a certain part of this object, not the whole thing. This is the first list of first column of the list that the base model is outputting. I know it's a little bit complex and then a little bit hard to wrap your head around. You have multiple layers of information, like this is number 2, 1, 2, 3, 4, 5, and this is like maybe X, Y, Z, I, J, K. What it's calling is that we only want not this one, because number 1 is actually number 2nd. So in human mind, this is 1, 2, right? But this is 1, 2. So we're only harvesting this column information from the output shape, and then put this into the base model. Put this into the input shape, not base model. From the base model, we only harvest the 2nd column of the information and then put it in the image shape. And then we flatten this information and then add it to the top model. Yes, that's clear, hopefully. Once we run all this, if you don't tell your computer to save this information to a specific manner, it wouldn't save it. So whenever you're done with this function, you have to return a value. Return means that you're going to output that specific value outside of this function. Function is existing within, so this is your whole coding environment. And then we already like defined a lot of like variables here. And the function is a very discrete object within this the coding environment. So unless you say, oh, you need to spit something out, and then like it will spit something out, and then that we will be able to use this value in our coding. Okay, so that's why we're going to return a certain value. It's going to be model. This is another function that we imported. Where is it? Right here. Model. Input equal base model not input. Outputs equal top. So based on this, there is a big brother called M, and then there is a older brother called the top model, and then the base model, and then the base model always gives something to the top model, and the top model always gives something to the big brother M. So it's kind of a hierarchy: B to T, T to M. Okay. So now we build up the basis of the
Sanghyun,
yeah.
I think you have an extra I in base model.
Yes. Base. Yes. Is that what you're calling out?
Or was it okay? Yeah, that's what I.
Okay. Great. Okay, so we covered quite a lot. So I'm going to suggest a 15-minute break, just like yesterday, and then once we come back, we're going to code how we're going to bring our own image, and then how we're going to activate that image, and then how we're going to generate the TSNE and then make that fit into the grid condition. Okay, sounds good. Okay, see you in 15 minutes. But if you have any questions, I can answer that in the meantime.
Quick question.
Yep.
For line like 14, 48 and above, like you always have the double quotation, but in, I don't know, like even for the lines above,
Right here?
yeah, like even up, could you go up? Yeah, like 28, like after help, you always have the double quotation, but when I type, there's only single. It's only single. I don't.
If you do the shift on the quotation mark, you can have it double quotation mark.
Oh. I looked up the import are parts, and then after help it also has single. I'm just wondering, like, what's the difference?
Okay, what's the difference? So double quotation mark is always used for the string. You remember my explanation for the string, right? String is usually for the text information, and then whatever that's in the single quotation mark is to define a variable. To define a variable within a function. So this is a function, right? Parcel dot add argument. That's a function. Function always has this like a parentheses. And then these are the variables that we're setting up within this argument, right? And we're clarifying what kind of a type of that syntax is. Yes?
Yeah.
And then the help is purely for human. This computer doesn't care. We don't have to have this. This is just to assist us. So to speak in human language, you have to use a string. So we're doing double quotation mark and then the directory of the output image folder. It tells you what this is. I see. You see. And then here is the same value error with the double quotation mark. Output grid dimension 1 by 1 is not supported. This is for you to remind yourself that you cannot make a 1 by 1 grid in the TSNE condition, right? And then to answer your question about this the colon right here. You remember in the Java we used actually semicolon, right, to indicate where things are ending. In Python, you don't have to always end it like this. You remember in the Java, you always had to end with the semicolon, right? Whenever you were done with a certain definition. But in Python, Python's a little bit smarter, let's say. So you don't have to always have it, but then whenever you have an argument, if it's an argument, right? If is a conditional statement. If it's a conditional statement, you would have to have the colon to indicate your condition. This is your condition from here to there. Does that make sense?
So the raise value arrow is just gonna be a text warning me.
Yes.
that-
Yes. Exactly.
But if that happens, the computer will already kind of crashed.
No.
Oh.
It's raise means that it's, you know, like you know what it means in English, like raising a flag.
A hand?
Flag. It's like it's literally like raising a red flag for you before it goes into a coma. So it will stop that process, or preventing you from going to a wrong direction and then keep hitting the wall, right? If you don't know what's wrong with your code, you will keep trying and keep running, and then like you're frustrated. Is to save you from that frustration, but also at the same time to prevent the computer to go into the limbo. Because if computer has something to say or something to do, it stops the calculation instead of keep doing whatever that's not possible. Does that make sense?
Yes.
Hopefully.
Thanks.
I know it's a lot. Yeah, you don't have a lot of like coding experience, right?
No.
Yeah. I'm trying to cover as much as I can, but especially for this particular part, it's really hard to understand the full picture. But then as long as you keep trying to understand like this and that, I think you will actually learn a lot just by doing this. And then when you look at more simple Python code next time, you will actually think that, oh, like it makes sense. This is not that difficult. I hope so. That's how I feel about having to write this code on my own. After this, oh yeah, I mean, I feel like I learned another language. It's same as, you know, learning new like language. For instance, like you're Chinese, right?
Yeah.
Yeah, like you had to learn English, and then when you first learn English, you're so frustrated and you don't know what this word means, and then you don't know how to do grammar, you don't know how to write, you're afraid of speaking English in front of other people. Coding is the same. Yeah, it's just a different language.
Okay. Thanks.
Okay, yeah. See you in like 10 minutes, right?
Okay, Professor, I'm not sure if I should ask this question now, or because it is about the program we run yesterday.
Okay.
I still have some issue with that. Do you think now it's okay, or we can do it post the class?
We can do it after class, I think.
Okay.
Yeah, sounds good.
Thank you.
Okay. Okay, we're back, and we're going to now start. Yeah, load our images into the system, and also we're going to activate the loaded image, and we will generate TSNE, and we will save that TSNE images image, and after we're all done with this hardcore coding, we're going to integrate all of this into the Google Colab a little bit more clean, and then we are gonna run our own code. I'm running a little bit behind than what I think, but I'll try to motor through a little bit faster than what I have explained before. So please please stay awake, and we'll make something cool at the end of this class. And tomorrow it will be much more visual and much more intuitive. So hopefully tomorrow will be easier class for you guys, and then you can have a nice end result at the end. Okay, so I'll start again. We are going to make before I start, is everyone here? John is here. Yeah.
Yes.
Okay. Yeah. I'll keep going. That load image. This is a new function, right? And this pred image is just another function, and we want to. You want to make this the larger bracket, the large bracket instead of the regular bracket. This is for the list. This is conventional for the list instead of a single variable in it. So usually for this one, you have like A, B, C, and then it means this exists as an independent variable. But then if you put something inside of this larger bracket, A, B, C, this wouldn't have this small quotation mark, and then this will be treated as a list. So what's the difference between the list and the non-list condition? You would treat this as an independent variable, whereas you are able to call this whole block as in one thing. So you can call this capital A, and whenever you call capital A, all of this following will be treated as one like a single object, but the single object that has multiple branches. So it's like a tree. So this is like a tree or obelisk that's like has only one direction. It looks a little bit weird. Sorry for my drawing, but this one is more of a tree, right? A, B, C, D. So that's the difference. You know, if you're familiar with the grasshopper environment, the the data tree. Data tree actually acts as a bunch of a list rather than independent variables. So you are storing multiple multiple array of a list in a data tree. The reason why it's called the data tree is it's actually a tree that's made out of the data. Okay. Grad image, and we're going to write some function. This is a way of write a for loop in the Python, and I'm using F here, but you can use I or whatever. It doesn't matter. Actually, for this case, it matters because F is going to be the variable that should be defined for the pred image. So we're writing a for loop inside of a list. So whatever that's going to be generated by this for loop will be included in the in this list. F for F, so F for F here, it's reading as a both F, but then this F and then that F is same and different at the same time, because you're self-referencing. So whenever there is a one cycle of a loop going on, the F that you're defining here is the F of the past, and then here, what you have here is F of the future. You get what I mean? So you're self-referencing it. So whenever you, so let's say F, this is a function for the F. F equal F plus 1, then what happened? Like in the beginning of the loop, like F was a 0, but then after one cycle, F equals 1. After another cycle, F equals 2. After another cycle, F equals 3, right? So this is a little bit confusing, but then when you think about it logically, it makes sense. F for F in OS lister. Lister is the list of a directory. You would have like thousands of images or hundreds of images to make this TSNE work, right? So it's listing all the files that's in your folder in that directory, and then the basically it's going to be a very precise and meticulous secretary. Count each individual photos that you have in that folder, and then make a list of the images, right? So this F is the short for the frame, how many frames that you have in this image, and then it's counting how many images in the folder, and then make that as a frame. In the so whatever that's the images that's inside of this inder, inder was a short for the in directory, right? Whereas inder? Yeah, inder is an arg in arg directory of the image folder. Images folder, that's more. Yeah, inder. So we're doing that for loop. If okay, that's good. This is file is function. I can show you. The os.path.is file is an inbuilt Python function that returns the true if the path is absolute path name. So it's checking if your directory is correct. Okay. So if your directory is true, you're going to make all this list inside of you for your image, the number of images that you have in the in directory folder. Does this make sense? Okay, I think that's that. And we're going to make a bucket that's called the in this image collection. Please note that I'm using this bigger parentheses rather than this parentheses. Whenever I'm making this bigger parentheses, it means that I'm making a list, right? It only makes sense because we already made a list. So if you're made a list and then trying to fit it into a very small bucket, it wouldn't fit, right? Because if you're writing equal small parentheses, it's just one value. But then if you're making this big thing, this bucket is infinitely big. So you can, and also it has partitions in it. So you have one thing here, 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 one thing here. But you cannot fill all of these objects inside of this thing, right? It can only fit one thing inside of this parentheses. And for this image collection, this is currently empty, right? What we're gonna do is that for IDX, short for index, and for image is just like a short for IMG is just for the short for images. Enumerate thread image. So enumerate is a mathematical function here. Enumerate method as a counter to an iterable and return it in a form of enumerating object. This enumerated object can then be used directly for loops or convert it into a list of tuples using the list method. So when you look at the example here, they made a list here, right? This list has eat, sleep, repeat, and then this is just a single string that's called geek. Object 1 enumerate L1. What does it do? Let's see. Type obj1 was calling for the enumerate this, right? And then print list. When it's printing, it's basically quotating all the sequence of this list. Number 1 means number 0 here is it. Number eat one, and number 2 here, which means number 1 in computer language, is sleep, and then number 2, which means number 3, which means number 2 in the computer language, is repeat. So it's basically annotating each individual objects in the list to have all this like tags, numerical tags. That's what enumerating does. So you could be very precise and meticulous in the organization when you use enumerate. Okay. Image equal os dot was dot path join in the and image and but what I just wrote here, you're using this enumerating method. We're basically giving it all the numbers for the old images that we harvest from the in their folder, and then putting it in the bucket named image collection. Dot append is a universal function for the Python. Whenever you say append, appendix at the end of your writing paper, like there's a always like a index or the appendix page with all the your references. It means that whenever there's a new thing there you're referencing, there's going to be line edit sequentially. It's basically doing the same thing. It keeps adding something in the bucket called image collection. Does that make sense? So all this loaded image from the in there with the image tag will have targeted size of outres. We already defined the outres on the top here. Outres was the argument resolution, and then resolution was the resolution of an input image. So if your image was a 128 by 128, it's going to search for this targeted size image and then load that as a targeted size of the image, and then append those images into the image collection bucket, right? So that's one thing. And then the just to make sure that we're collecting the right thing, we want to have some mathematical the equation to check the validity of this. NP square outdim means the size of the grid. When this is smaller than the size of the image collection, what happens? This is the total number. You have total number of 100 images, and when you square root it, this is 10. So the total number of the image here is 100, right? And this is actually not a square root. Sorry, this I'm just thinking ahead. And then this is the out dimension is a 10, let's say, or let's say this out dimension is 13. You want to have a 13 by 13 grid, but then you only have 100 images. Then square of this is the what is it? 169? Is it 169? No. Yeah, 169 is 169. So it's going to be 169, right? So over here, this is 169, and then this is 100. So this is bigger. You don't have enough image to make the 13 by 13 grid. Then computer run into an error because computer cannot make up an image to compensate for the whatever missing in the grid. So in that case, we want to raise a flag, value error cannot fit X number of images in X by X grid, and after that, format len is short for the length. Length is if you have 1, 0, 1, 2, 3. So, and this is A, and then len A is equal to 4. So it's a total number of the total size of your length, your list. Len. Right, so it's raising a flag, basically saying you can't do this. Why are you doing this? Don't do this. And after that, we validate the whole process, and now we can get the clean result from this function. And as I said before, whenever you're ending your function, you have to return your value. In this case, most valuable thing to harvest is most valuable and only thing that we want to harvest from here is the image collection. Right? So return image collection as a list. All right, so we have finished loading the image theoretically, and now we're going to activate these images. Yep. So through this get activation, we're using these two variables, one that was defined in the build model, and then the one that was defined in the load image, right? Both of these are the return value from the previous thing. So this is the process. You build one function, and then you harvest like one thing and another thing, and you make another one, and then there could be another set of these things, and you make another one, and you combine these, and then you have another one. So this is quite boring process, but then quite necessary process to deal with complex data structure. And don't forget to put the column here after. And on this case, we're going to also go through the same process as we made this empty bucket called image collection. We're going to make a bucket called activation. And of course, this will be in the list form of a list activations. And for this one, the same as index and image here. In index image in enumerate image. Index is when you repeat the two, the equal mark, that means it's an argument rather than a definition. Okay, so if index is equal to plot, where is to plot? We defined before to plot. Yeah, here to plot. If this is equal, and I'm going to call out a break. Break is you give it a break to the calculation, and then give it a stop point. It's a stop sign, and then we're going to because we want to make sure that your image is getting processed. So I'm going to print out the message called processing image number whatever, right? And this format is always used as an insert into this the medium-sized bracket, and you would see index starts from the 0. If you don't predefine it, it always starts from the 0. So first for loop is index is a 0, right? And then there is no such thing as a processing image 0 number 0. So that's why we're adding number 1, so that when it's processing the first image, you will see the message saying processing image 1, right? So this is for us, for human being to have a less anxiety and check if it's working or not. So now it's going back to the taking care of the machine. Image resize. This resize is the basically embedded function in the image tool. One of the image tools that we're using in here, the pillow, and the image resize to the target size. So for this particular case, because this machine learning, the component was trained under this specific circumstance, it wants to have a 2 to 4, very peculiar and special case, but then we want to make sure that this is 2 to 4. So we are going to resize it to 2 to 4, but then also we're going to use the image dot and with the all cap Anti-Alias. Those of you who plays game, you probably know what Anti-Alias means. It's basically super sampling if you have, let's say, 4 pixels as an original image, if you do anti-aliasing, you can make it look like it's like 4 by 4 rather than 2 by 2. Does that make sense? It like make a subdivisions and then make it look like it's a high resolution. And I'm introducing this the variable called x here for image to array. This is a function. Where what it does is that the image was an independent image that was included in the list called the image collection, right? Now we're making this resize image into the array again because it was in the bucket called image collection, and then we actually pull it out again to resize, and then we're basically putting this back again by using the image to array, right? And x equal np expand x is 0. So numpy extend where's numpy extend? Right here. Expand the shape of an array. Insert a new axis that will appear at the axis position in the expanded array shape. So it's introducing additional dimension to your array. So for instance, if your image is just a linear information, it only has one directionality. But then once you introduce another axis, you can suddenly have image that's overlaid or laid down like this, right? So this is what we want to do. So this is why we're going to use the expand dimension. And we are processing this image again. Pre-process input. This is just another procedure to make sure that your image is all good. Activations, append. You know, this is pretty much the same process here. We're just putting it back from, you know, was image collection. We did resize, and then we put it back into the some sort of array. But array is a little bit different from the list. Array is just like the things that's just not in the order, right? And we're putting this array into the new bucket called the activation. So that's what I'm doing right here. We're just changing the bucket after we did something. So you cook an egg, and then you put salt, and then you put too much salt. So you want to change your I don't know, your pot or something. So you're basically keep changing the pot. The original ingredient is the same, but then at the end of it, at the end of your process of cooking, your egg is not just an egg anymore. Maybe it has some other green stuff. Maybe you would want to add like I don't know, broccoli or avocado or bacon. You name it, right? We're basically cooking here. append, we're doing another NumPy function called the squeeze. It's like literally like squeezing your data into more of a compact form. I wouldn't go too much into detail about the explanation. You can just think that this is simplifying your data X into something more of a compact. And now we can return. Make sure that after your if statement, this return is not staying inside of the return and if statement, but that it's at the end of the for loop. Okay. Yeah. Return activations. So now we're storing activations as a list, right? So now that data is activated. Now we want to create a TSNE. Generate TSNE activations. TSNE equals TSNE. This TSNE with the capitalized letter is the function, and then the TSNE that's in the lowercase is a variable. Okay, this is variable. This is function. Function usually comes with the parentheses. I always get this wrong. So perplexity is equal to perplexity, because we already did this. This is the name of variable that's required for the TSNE to run, and then this perplexity is a perplexity that we defined earlier on right here. It is confusing, yes, but then this is how we do it. Perplexity is equal number of the component components is 2 init equal random. These are some of the required variables for this to run. You don't need to know what I'm exactly doing for this one. If you want, you can go into their API and then read what this exactly is doing, but you don't need to change this ever unless you want to be explorative. And then the x2d, this x was an the array of information or list of information that already has an additional let's say axes, but then it wasn't still defined as an two-dimensional array. So we're trying to make this x, this like activation, a list of activation into a two-dimensional grid. SNE dot fit transform numpy dot array. It's literally making an array of information from activation, a list of activations, and here this is a lot. This is just defining what goes inside of this array. So that's 0, and then to plot is going to get in, and this is an the empty column that's going to go after. Here I'm going to use this a new syntax, which is a negative equal. You'll see what I'm doing here. Just in a second. 2d dot minimum, short for minimum, x is equal to 0, and then the x to the plus equal. This means like you have a reference point here, and then whenever you do negative equal, you're basically referring to this one, and then whenever you're doing plus equal, you're referring to this one in the one-dimensional array situation. but we'll get to how we are defining exactly how the two-dimensional condition is. X is equals 0, and x to b. So now we have generated TS_any grid. I mean, just TS_any, not a grid. Now we're going to generate the grid condition. Okay. Actually, we need not just this, but then more information. Image collection and x2d and outres and out dimension. So we want all the image collections, which is the collection of images, literally a collection of images, and then x2d. This is like a information that was generated by the TS_any as a vector information, and then the outres is the size of the our input images, which is 128, and then the outdim is the size of the grid. Okay. We are missing a column here, and here we're instead of calling this why am I just saying like say the grid condition, but why am I typing the generic I guess it's late. TS_any grid, save TS_any grid, because we have all the reference points for all these TS_any as in that the location of these like reference points for the image, and then we're going to use image collection to make that as an image, and then so these two are used, and then the outres is defining the size of this image, right? And then outdim is how many it's going to fit within this box. So all of this is the ingredient to cook the entire the image assembly. Grid equal MPD stack. Just making a stack of a two-dimensional grid condition, and inside of that mesh grid. Mesh grid is setting up a grid to establish the grid condition. MP linspace 0, 1 out. 0, 1 means from here to here, the distance is something, right? This is the grid number 0, grid number 1, and then the distance between that point and that point is 128. We're defining that through this, and then we're defining that defining the size of the grid with this function. So there's always 128, 128, 128, keep going. Okay, and we're going to reshape this by -1, 2, and cost matrix is it's just another function that we're going to call, another variable that we're going to call out, and then we're going to use the C distance. We are already using the grid function here. I mean grid variable here. X to if this is indicating what's the name of the function that we're going to use for C-dist calculation. This is some guy, some mathematician's name, or the developer of this algorithm his name, and we're going to borrow his power to calculate this distance as type and p dot. If you're wondering about what this is exactly doing, you can read it on NumPy or see this. This is the float 32 is basically making the, there is like a 8-bit, 16-bit, 24-bit, 32-bit image conditions. Usually your image in the RGB world that is like a most basic is going to be I believe 24 or 16 or 24. And if you're saving it as a high resolution, like a JPG or something, that's going to be like a 22-bit. I mean 32-bit. So it's basically making a float that is in the 30-second rule rather than the binary rule. Does that make sense? So it's defining a type that is in the form of a 32 bits. I know it's a little bit hard to understand. It's just calculating the matrix with the C distance using this equation in the type of a 32 bit, right? We're again using a self referencing system. Cost matrix is equal to the past cost matrix self to multiply this by, in this case, I'm going to set up 100,000. This is a set value that is optimized for this the specific code. So I would not recommend changing it. Or if you're going to change it, you want to write it somewhere, write it down somewhere so that you can change it back to original state. And here now, raw S's, column S's. This is like a raw S column S, and lab JV. This is a specific the variable type that's necessary to run the lab JV. Post. Oops. We're going to use that the result of the lab JV is grid JV is equal to grid whole column assets equal NP1s then okay, and then I'm missing one thing here that should be good. So when you search for the NumPy1s, NumPy1 return a new array of a given shape and type filled with ones. So if NumPy1 is 5, you're just adding 1, 1, 1, 1, 1. It's just I guess like in easier term, is a filler that is like creating an emptier, more of like a field array that's with the 1. But then in the exact the length of the list, that's what we're trying to do here. Pose is a position of the position within like a vector space. And since we have already defined all this like a distance and everything and the set up the grid and all this shit, so we're going to define the position and then the image using the position and the image, and then place this in the TSN grid. And image collection from 0 to plot. To plot is the maximum number of the images that's required to plot the array. So if this is a 10 by 10, to plot will be 100, right? Because you need 100 images to fill the 10 by 10. And to the column here, and H is the height range equal to integer MP floor. You're literally like flooring it onto the XY plane. Columns position 0. Multiply by out dimension. Out dimension is the size of the grid, right? -1. Multiply by res. I showed you this calculation in the beginning of the today's the workshop, right? Height range is you have a number of these steps, which is your out in total number is going to be your out dim, and then this is going to be your out res, right? And then the position here is basically referring to the position 0. And then in this case, position 0 is X, and then position 1 is Y, because the pose is referring to X, Y, and then all these things here is 0, all of these things here is 1. W range equal, this will all the same, will be the same, and it's just going to change here as 1, right? Because this is width and this is height. So like this, if in the conventional world where X is usually horizontal and Y is usually vertical, width is actually pose 1 is X, and then the pose Y is actually Y, right? And out, this is the output H range. Plus two, we're going through a very similar process we did before using the image array function. We're just putting it putting it back to the new bucket. Here, IM is equal to image array to image out. This out was defined right here, right? And then this is to express the grid condition, that is by increment of the 1 to 8 pixel, 128 pixels. And then as a result, we have this as an array information with the two-dimensional the strings, and then that's going to be output as an two-dimensional array of the image assemblies, and we're calling it as an IM. And then that IM, we have finally have the result for the image. Image saved is out. We have to save it, right? Save outer plus out name quality is equal to 100. Like this you can change later on if you're having problem with the memory issue. You can have it as a 50. That's fine. It's just going to degrade your image quality. You would have a memory deficiency when you're trying to run big size of the image, big size of the image assembly. And we define all the necessary functions here. So now we're going to define or assemble all this function into one main interface. So we're going to write the function called the main. It's quite similar to the setup in the Java main. Model, build model. Image collection. We're basically redefining all these functions that we used here. From the build model, we're returning model. From the load image, we're returning image collection. We're just making sure it's like a fail-safe. From the activation, we get activation. From the generate TSNE, we get the 2XD. From the save TSNE grid, we have the image save. So we're just repeating these. And to indicate that your computer is working on it, we're going to write this statement saying generating 2D representation. Okay, and then the X. TSNE. And we're going to say print image grid. Okay. And save. Image. These are all the essential variables to save the TSN grid. So here we're basically repeating these at the end just to make sure, because we're calling out all of these functions again in the main. If we don't call it out, it's just not going to run on its own. We have a function. Function is a tool. If the tool is not used, it's not really tool. It's just an object, right? It's the same thing in the coding. So we're calling everything one by one to make sure that it's all working. And then when it's working, we're going to indicate what it's doing, and then at the end, it's going to say, once that's saved, we're going to say if. This is with the 2 underscores, name equal to name. This is basically to make sure whenever we call out this function, we execute this main function. This is to execute this main, right? If your name is called, you start working. Same thing here, right? But by activating main, we don't have to call out each individual function one by one. It's going to be just one simultaneous process, continuous process, rather than activating each individual function. So now we're actually done writing this. So we can either run this on its own, but I wouldn't recommend that. I would open, I mean, if you have your own, let's say, like, I mean, we already have a processing code. So let's, where's my processing? Okay, we are on the processing. We're going to open new and then make sure this is not in Java or using Python. So change your environment to Python and copy this all in here. And then save this as what should I call it? PSNE grid.py. .py is an extension for the Python. I'm going to just save it on the desktop. Okay. In an ideal world, we wouldn't want to just use the processing. We would want to use like something like a PyCharm. PyCharm is like something like this. It will help you write all this the code. But I didn't want you guys to just download extra software because we're already using so many. So we're just using this as an environment to introduce the working within the code writing environment. So once you have that, I'm going to close all this numpy stuff. Okay, and now you go to the TSNE grid, call up TSNE in your Google Drive, and then in that, if you have done the process already, we already made this the directory, right? In that directory, I already have it here, TSNE grid.py. Just drag and drop your the code inside here. I'm going to just delete this test one because that's something that this is going to produce. So instead of doing all this, we already copied and saved it somewhere, right? So we don't need this anymore. So I'm going to just delete this, right? And then I'm going to show you better way to do it, more like clean way to do it. So whenever you're calling out a Python extension file, you do the expression mark with the Python, and then after that you have one space, and then you call out the name of that file, grid tsne grid.py, right? And then after that, this is where the argparse is very useful. Instead of the spelling out everything, you can either say dir with the 2 hyphens, or one just a one with one hyphen D. But for clarity, I'm going to just use the dir, which is the directory of your file. And then for my case, I already have a folder called the image 128. Image 128. And I'm going to call that directory out. We already set up the directory. It is CD is short for change directory. And then we're already in this folder. So we don't have to spell out all these things again in this environment. It is, your computer is already in this folder, right? So you only have to call out the name of the folder. Third, image 128, size is equal to 10. Name is size means the grid size, not the image size. Okay, the grid size is 10, and then the name will be let's say I'm going to call it df_1.jpg. And then my resolution. I usually save my image with the size of the input image, so I don't get confused later on. So I'm going to put the resolution of the 128 here, and then here per is for the perplexity. I'm going to leave it at 50 for now, and then iteration. Because I'm just trying to demonstrate it, I'm going to have a low number. 500 is not that big of a number, so I'm going to use this one, right? But before that, I need to make sure that I'm connected to the Google Colab. Sometimes, if you don't run anything for a long time, it disconnects automatically. So I'm going to reconnect this. Yeah, I'm connected, and then to check. So I'm working on 2 hours ago. Like, you don't want this, right? You want to terminate this. You only want to have one, and then you can see that you were connected with the GPU, and you want to go through each individual tabs whenever you reconnect it. So I'm going to reconnect to my Google Drive. Allow. Does anyone have their own data set? If you have, can you let me know? So I can test out your images on my computer, or if you want to run your own, I can help you.
Do we need to upload that to the Google Drive?
Yeah, I'll share the folder that everyone can upload their own. At the end, it will be actually fun to put everyone's image into one TSNE, and then as a whole class, I can make a whole image assembly to represent our class to the digital future as well. I think that's a fun idea. On here,
I think that's a good idea.
right? Yeah. See, yeah. Get very excited. Yeah. Okay. So I'm going to share this the folder, and then you can just write down your own name, like Ife, Canu, Carlos, John, Alejandro, Holly, like everyone. Like, if you have your own data set, upload it to here. I'm going to share everyone editor. Great. Okay. Okay, so like I ran this, but then it's saying now error message, say from labjb import labjb module not found error, no module named lapjb. This is a bit of a problem, but this is nothing that we cannot resolve. So before we run this, we just need to make sure that the labjb is installed or imported into our the environment, right? So how to do that? It's easy. You just with the expression mark PIT. That's the kind of shortcut for telling your computer to install this certain API services. So install labjb, run this, and look at it. Like it already found where it is, and then collecting labjb automatically is somewhere in the web, and then the downloading it, and amazing, right? It's very seamless between one to another. So it's already successfully installed. So now let's run it. Let's see what it's going to make. It's always give you this warning, TensorFlow, you're using like older version of a TensorFlow, and then they're going to scare you. They're, you know, they're saying like, oh, we're not going to support it in the future, so be aware. But don't worry about it. They're going to support it. But you know, now it's downloading data from the deep learning model BGG16. So all this like import setting that we had in the file in the code is now actually trying to install all these data from the somewhere on the internet, so that it can run all these different functions within their environment. Okay. It's running. See, like it's processing image. It's already finished. But sometimes it takes time to save image. Okay, there you go. See, it already created this like a 10 by 10 image, but we can increase the number of iteration, number of the grid size, and all and so on. Let's try again with the bigger size. I mean, perplexity we don't need to change, but then in terms of the size, let's check how many images that I have in this folder. That's everything. Oh no. Like it's too much memory consumption. Page. I'm gonna reload this. Actually, can check it in my own drive. It's probably faster. Well, you know what? I'm just going to guess this and let's make 30. If it doesn't work, it's a good lesson, right? Okay, it's working. Yeah. Yeah, it's generating representation. This was at the F1. I actually didn't change the name by accident, right? So what it will do is that it will override the image. So make sure if you have a image that you really like, save it somewhere else, or next time when you run it, you change this to like DF2 or something else. Okay. Now there you go. Yeah. You see, like this is now 30 by 30, and creating a nice image. So you can do the same thing with your own image set. Yeah, you write your own code, and then you're now generating this like a image assembly. Yeah. Has anyone uploaded their own data set yet? Okay. When Zoo, is this you? Someone in the class? Oh, look at that. Look at that. How many images is this? Holy Zoo. Okay, Holy Zoo. So, once you upload this to my thing, I can get a link to this. No, actually, no, not this. Add shortcut to drive, and then I can save this shortcut in the Google Colab. Call it TSNE master, and I can just add the shortcut here, and then without downloading it or changing the directory, I just use the shortcut to where is it? Image. No, okay, here. You see, like this is now in my the TSNE TSNE folder. So now I just need to change the directory here to, what was it? 11. How many total images do you have for this one, Holly?
I got 1024 and maybe it's and 8 and 60. Let me check.
So 3, 3, 8, 8 by 1, 2, 3, 4, 5, 6, 7, 8. 8 by 8. Okay. 8
Yeah.
by 8. Yeah, great. So we can do this size of 8, and then we're going to call it Holy 1. And then the resolution is what? Like 128?
Yeah.
Great. Yeah, let's try it. Why is it taking so long? No, I don't want one of these things. Just want one. Okay, 20, 25. Okay, it's finished. Great. Yeah, look at that. Yeah. I think that for this case, because everything is in the very similar color scheme, it's maybe not creating the most accurate conglomeration. But once, if that's the problem, you can actually increase the iteration number. I'm going to bump it up to 5,000 and then run it again. And I'm going to call this it. And also the size of the your data set matters too. If it's only 8 by 8, it has a little bit of a limitation in terms of seeing a pattern, right? Once you have like this like 30 by 30 grid, you can clearly see like how the data is like forming in terms of as in pattern. But then 8 by 8 is a little bit difficult. But you see, like when you increase the iteration, you're now seeing more of this like the same thing in the more of a in the same spot. So you can play with this iteration number and then the perplexity, and then find the best spot for your data set, or just generate whatever you think that is the most suitable for your application. I actually didn't change that, so let's see how this will get updated. To make sure that I'm seeing the new image, I'm changing this to this, and then also I'm going to name perplexity number 20. Okay, finish. Sometimes it takes a little bit of a time to communicate between the Google Colab to Google Drive. Okay, there you go. Yeah, like you see, like this looks like more, I mean, better representation of your data set pattern. This is all segregated on one spot. So it depends on your data size, your perplexity optimization. You have to figure it out on your own to make sure that everything works in your favor.
If I want to put I already submit a different path in the file, and if I want to combine the different file into the one graph, but their name is.
Oh wow. Okay. Yeah, many. Great. Okay, I'm going to download all this and then to combine all this into one thing.
But different. This is the 256.
These are 256. I see. Yeah. Okay. Okay. Yeah, I'll make sure that I exclude this one and then yeah, combine all this. But did you follow all the code writing part that I covered? Have you tried this on your own computer?
No, I'm late today.
Okay. Yeah, but yeah, try it on your own. It's going to be different if I'm doing it for you, or you being able to do it later on, on your own, right? So make sure
Okay.
to follow this again, and yeah, try to do it on your own.
Okay.
I mean, if I'm here, I can like troubleshoot all these small issues that for you to take like hours of your day or days of your life. I can probably solve it within like 10 15 minutes. So just use me when I'm here.
I will try today.
Yeah. You can also ask me questions tomorrow
Okay.
when we start.
Thank you.
Yeah. This one. Okay, this is in total 112. So okay, we can do 10 by 10 grid. I'm going to set this up into different 56 and yeah. 2. Putting 62 items. And in the meantime, I'm going to download other people's. So Ife and then the Quan Yu. That's you guys, right?
Yeah.
Okay, that's complete. So I'm going to run it. Let's see what you guys have. What kind of cool things do you have? Still sitting fine. Is this like some big data set? Ooh.
Oh, this went because I was not able to run the yesterday's program. So
the
I
cut?
didn't really,
Yeah, that's fine. Oh, this will be interesting. Is those like a traditional, like a painting for the wooden structure, right?
Yeah.
Yeah, wooden structure. Good. Cool, very cool. How many photos?
300 something.
300.
So like, I'm not sure whether the origin. I didn't like resize the original photo to that's empty.
This is 128, and then you also have a 200.
No.
Okay, you don't have it.
This is 256.
Oh, is this Monet?
Yeah.
Cool.
Both of those are 256.
Okay. You guys are greedy. You want high res photo. Yeah. Okay.
Should I try 128 instead?
I want to see this one first. Okay, yeah. Yeah, it's creating something. Yeah, it looks like a octopus leg here. What is this original image? Holy.
Yeah, it's not the artist. It's not a famous artist. It's like the type like flat flat 5. Yeah.
Okay. this is it. Yeah, this I need to cut it, so I'm gonna do this later, Quinn, with you after the official class is done. That's good. Okay, I messed it up. $338. So you can do 18.
Is it better just to resize to a square like the original image so that we can have the perfect
This is square, no?
yeah, like the original image.
But that doesn't matter, yeah.
Oh.
Yeah. You're hoping that it's all going to be perfectly like.
Yeah.
But no, yeah.
So as long as the number is larger than like because you're doing the square root.
Yeah, so I'm doing 18. Yeah, 18,
Right.
18 by 18. Yeah.
So
Actually, like let's say when you have let's say 3,000 images, the maximum number, how many is that maximum number? Maximum number that the grid number is 54, right? But then let's say you're running only grid size of a 30 by 30. It actually gets more interesting because you will see how like computer is picking a batch of an information in that like large pool and then generate different image every time. So like this is something that you can think about it, how you design your data set and how you're going to use it to best represent your data set or create kind of different composition of your images with just a big pile of a data set to create different types of aesthetics.
I see. So like the more variation, the better for the aggregation.
Yes. And tomorrow with these assembled images, we're going to do tessellation. I think, especially for these kind of like, non-architecture images, I'm super interested in how this will register in the tessellation method. There are different ways to do it. It depends on how much time we have. We're going to, oh, look at that. No, it's pretty cool, no? Segregation happening with the similar color scheme, similar pattern. It's pretty good, right? Like it's recognizing the pattern where the location of these, like these are where the intersection happening, right? In terms of a loop choice.
Yeah. So
Yeah,
like
yeah.
creating that kind of.
Yeah, this will be super interesting to put it in the tessellation. Yeah, I'm super excited. Yeah, thank you for preparing this. And I mean, also for this one, for a different reason, because this looks more like a kind of biological, you know, more organic form rather than rigid geometry. And I wonder how this will translate in the tessellation tool that I have, because I developed it for the voxelization in the Houdini. But there are some ways to smooth things out. So let's see how this works out tomorrow. And for Houdini, it will be a little bit easier to follow. So tomorrow, I really recommend you follow through my tutorial as I go by, so that we can look at the results of the Houdini at the end of the class all together. So that you guys leave this workshop with something on your hand. I don't. Oftentimes you think that, oh, I'm gonna watch it later, but you never do it. You never have time. So I want to make sure that's the case. And also, for tomorrow, if you want to bring more images to have a more, diversity in your data set, that's perfectly fine. And then for those of you who haven't submitted your data set, you guys can submit your own data set tomorrow, and then I can run it quickly for you, and then you can use that image for your own tessellation. If you don't, we can just, I can just share you my images to work with. So that's perfectly fine too. Okay. So how was the Python the code writing tutorial? Was it helpful for you guys, or was it too hard, or too slow, or too fast? Like, what's your opinion? I want your opinion about this. No opinion?
I think it was good. Oh,
It was
sorry.
good? Okay. In terms of a pace and in terms of the amount of explanations I gave, was it enough to follow or at least understand what's going on?
For me, it was okay. And
But you have
didn't have
some
to-
background, right? Some experience
yeah.
in coding, right?
Yeah, that helped definitely.
Okay.
And are you gonna share the script, or?
Yeah, I can share this Google Colab with you guys.
I was also wondering, yesterday you showed us some signs, and when you talked about how TSNE was developed for like language research, and you showed us some like a lot of images of signs, and I don't know if you were able to run it to test it.
Yeah, I really can't, but I didn't run the linguistic, but I can do it, just quickly, just in a sec. I'm going to share this.
Thanks.
And now I can upload the linguistic part. Yeah, symbols. I have 1,882. 43. Okay. And then the resolution. This is 64 by 64. Yeah, it's going to take a bit. So if you guys have any questions, I can answer them while this getting uploaded.
Oh yeah. So the question I have just about just to correct what I coded yesterday.
Yeah.
Because yeah, because I can run it. Okay, so I share my screen or something.
So let me actually, since you already uploaded your file, let me demonstrate the process again with your own data set. Is that going to be good for you?
Yeah. Yeah.
Okay. I already have it. Why am I downloading it?
But I think the email the amount of email is not big enough for.
No. Like let's see what can be done. So this is you with this. We have all these images. What's this? What's the resolution of these images? Yeah, this will be enough. I'm going to
Okay.
bring all of your images into my processing. Image, data. Actually, I'm going to do one. Two, one. 6, 7, 2, 1, 5, 27. Actually, I don't need to do this. I can automate this process while I'm doing this. Okay, from the Q1 to the Q47, I'm actually going to use a different tool to make sure that everything is okay. It should be fine.
Okay.
That's right. So here in the data, I have all of your images to name the Q1, Q2, Q3, and so on, and then up to Q47. I check your images and it's around like a 2000. Sometimes it's a little small.
They have different resolutions.
Yeah, but we're going to cut all these things into the 128. Doesn't matter what size your image is, it's going to uniformly cut to 128. If it's a larger image, it will have like a smaller kind of a voxel size. If it's a smaller image, it will have like a larger voxel size. If does that make sense?
Yes, sounds good.
Okay. And then it will make an overlap between a cut to another cut, so that you will have a more sampled image from one image, so that your overall data set will be very sizable. And then from what I gave you as a code, there are only two things that you need to change. One is the namespace, one is the outer. When you look at the outer thing, I know that you're using Mac, so I can't advise you correctly here, but you can just basically copy whatever that's here into here.
Okay.
So,
Okay.
So this is your out there, right? Out directory, and then you copy this and then paste it right here. But then you see that there is a backslash. In processing, backslash is not not good. So we're going to find all those backslashes and then change it to the forward slashes. Click replace all, and now every backslash is changed to the forward slash. And then you have to make sure that your end of the directory is kept out with the forward slash as well. And then at the end, you need to have a closing of a quotation mark and then the semicolon. Okay. And now we have everything set up. So I'm going to run this. Okay, that's a PNG. We don't have a PNG. We have actually JPG. So let's see if this works.
Yeah,
Okay.
it's like when I run the program, a window like this jumps out. So
Usually when I use the other code that I was trying to run, it will automatically change the JPG to the PNG. But if that's the case, sometimes just going into Photoshop and then changing the file format would be a good idea. JPG and PNGs are very different type format. JPG is a compressed format, PNG is not. PNG is more of a bitmap image. So
okay, I see. Yeah, I will transfer them to PNG because I took a picture and I directly cut them in Photoshop, so the format won't change. Okay.
so let's
Okay, so let me try this and try that code.
Yeah, so you know how to save this as a PNG, right? Just a quick export as a PNG.
Yeah.
Yeah.
Yeah, I know that. Yeah.
Yeah, so once you change this to PNG, you would have no problem cutting this image if you're using the code that I gave you.
Okay.
Yeah.
Okay. Thank you very much for resolving such a big issue.
No problem, no problem. It always that's a part of the process. And we're ready to run this. Let's run this. Sorry for going over a little bit. Symbols. So we want to call this symbols. All right. Some time. Because this is a much larger image, it's taking longer time to make the image size. Because when you think about it, the image size for the each voxel here is 64, and then you're multiplying that by 43, right? 43 by 43. That's actually quite a big image. 64 multiplied by 43 multiplied by 43 equals, that's pretty huge pixel, right? So that's why it's taking a long time. But now there we are. We see like it's like a organizing similar family of these like characters into one group, and then there is some intersection between the one language to another language, and then you see how the one language developed another one in terms of like a similarity from the one thing to another, one grid to another grid, which is quite interesting. Like this all looks like a this like a U shape, but then you can see that this is actually from completely different family, and then that this is the same. This is the same. You see that? So like it's actually pretty good linguistic tools to identify the similarity between one to another language. So let's say this ancient form of the language is found in somewhere in the Mesopotamian area, and then how do you relate that to like ancient like a Persian language, or ancient Persian, ancient like Turkish language? It's you can actually compare it graphically from one to another, and it will give you very meaningful results.
Good question.
Yeah.
Is the input image is smaller than the canvas size? Will the machine use duplicate? Like
No,
then it will be empty.
it will not run.
Oh,
Yeah, it will not run. Yeah, we made sure that it wouldn't run when we were writing a code. But one trick that you can do that could be quite interesting is that you can actually overlap an image on top of it another image. So you see that this is now not actually occupying a whole grid, but then there's always like a half of an overlap. You can change this in your code. So when you click this, Python file that you uploaded in the your TSNE Grid Master, and then you can open with the text editor here. Then you can change your code within this environment. And you remember where the part that we were changing we're setting up the grid here. You can change this number to make whatever overlap that you want to make. For instance, what happens if you do -1 to 1? I'm going to save it, and then when I'm not going to run this big one, but then maybe I'm just going to run 10 this time, and then this is going to be 10. So that it's going to spit out the result faster. Value error x and x1 must be the same number of the column. What happened? Let me write it down. So -1, 0, 1, 2. So that's a set. If that's the case, -2, 1. Okay. Well, I was going to cover this tomorrow, but then there are some modification that we can do to the code to generate like different types of aesthetics using overlap, using creating more spacing than it should be, so that it creates an interesting interstitial space or the interesting shape that's based on the kit bashing, like image bashing from one image to another. So I can definitely cover that for a very short time in the beginning of tomorrow's class. Okay.
Yeah, thank you. It's really interesting.
Yeah. Great. Great. Glad to hear that you guys are enjoying it, and it's your journey. Okay. So, any other questions before we go?
Yeah. I'm curious if you can try this algorithm with meshes, like something more three-dimensional, or is it?
We're
needs
going to
be-
create the mesh based on this image tomorrow.
Oh yeah, I understand that, but directly using meshes like with 3D GANs and things like that,
That's
or that's too complicated at the moment.
yeah, that's completely different work process from what we're dealing with here. What we're dealing with here is that we're let me share my screen just really quick. What we're dealing with here is that we have an image, right? And then this is like, let's say 64 by 64. And then each pixel contains a certain information. And then you're basically make this like 2D representation of an image into an vector, which is a number, right? And then we're correlating a vector to another set of a vector, and then calculating the distance. Let's say theoretical, not theoretical, but then like what is it? It's calculating the affinity from one vector to another vector, so that it decides which image goes where in terms of a location of these images. That's why I'm calling this workshop contextual assembly, right? It's based on the context that we harvested from around us, and then we are trying to reassemble it, rearrange it based on the machine's understanding of how one relates to another. If you're interested in, let's say, using it with the mesh, amount of the information you need to calculate for that is going to be way too heavy, right? Let's say if it's two-dimensional array like this, the total amount of the pixel that you need to calculate is 64 by 64 per one image. That's what, like that's about like 4,000 pixel information per one image. But then 3D is something that you have to calculate as a layer by layer with a very small interval. So that means that the amount of the information that you need to calculate under these circumstances actually not only just like twice or three times, it's like 9 times. Sometimes it's like more like 20-25 times. So it's technically like impossible to run the TSNE with the mesh.
Okay, yeah, it makes sense. Thank you.
Yeah. But the 3D GANs that you're maybe imagining what you would like to do is, I think that something of a more of a projection of an image from the multiple angle. Like you have it's like a photogrammetry, right? You have an angle of a photo that you took from here, and then you took another photo from here, and then you took another photo from here. And with these like a 3 to 5 images, you make a projection. Usually that creates a point cloud. A lot of the 3D game uses a point cloud as a starting point. And then once you have that point cloud, you're connecting dots from one to another and then assigning, and you can assign like a RGB color value into the point cloud. And then that point cloud, like each point that contains all this like the color information will now contribute to will then contribute to the make its own texture map. So it's actually multiple layer the processing. One is the geometrical information based on all this like points as, and then the calculating the distance between the point to the another point as a vector. And then another thing is you are averaging a color from the color information of the point cloud here, point, what's the average color between here and there. So you're like, it requires a lot of computational power, but then especially for the TSNE, it's not only calculating just the one object, but then it's trying to calculate the relationship between multiple ontologies. So it's extra difficult. I'm sure we'll get there someday, but not now.
All right, thank you very much.
Yeah. Okay, so all good. We went over a little bit. I'm thinking maybe tomorrow we might have to go over a little bit too. Maybe I will start a little bit earlier to help you guys like troubleshoot or anything. But I have to see. But I'll keep you guys updated for the tomorrow's schedule. Okay.
Thank you so much for today.
Yeah, no problem. Thank you for participating and preparing your data set. And yeah.
Thank you.
Yeah, great. Thank you.
Thank you.
See you tomorrow.
See you tomorrow.